Might take you a little time, but I think you can do it. I think you can do it. Okay, let's finish up yellow handout. Substituting a leaving group. Okay. Reaction A looks pretty straightforward. We got an ethoxy nucleophile. Can we displace that chlorine there on the ring? Has a strong electron withdrawing group, ortho-apara. Nitro is a common example of such a group. Can we say the nitro group is activating the chlorine for displacement? Yes, because if the nitro wasn't there, you would not be displacing the chlorine. So again, is nitro an activating group? It actually is for NAS. For EAS, though, it's a deactivator. Don't confuse your terms. On the other hand, if you react to the same conditions but have a methoxy there, like 2-chloroanisole, you're not going to displace that chlorine because that halogen has no, that potential leaving group has no strong electron withdrawing group ortho-apara, right? No reaction? Any other possible reaction? Yeah, question? On the other hand, if you do this reaction down here, see up top, those were done at room temperature. If you do it at 300 degrees, you can't get a reaction. And the ethoxy will displace the chlorine. But you get isomers. How do we get that product?
Benzyne.
Yes, let's look at that. Let's look at that. Okay, we were looking at benzyne. Benzyne, over here. Now in this example, I use 300 degrees, also use pressure, sometimes that is. You don't always need high pressure, but a lot of times. Because reaction time is not given. Maybe if you don't have pressure, it takes like 12 hours of heating at 300, but with pressure you can do it in maybe 1 hour. We showed a mechanism and it showed a benzene ring with a triple bond, alkyne. What do you think about that? You believe that?
Yeah.
You believe that mechanism?
Yes.
It's a triple bond in a benzene ring. It's supposed to be linear, right? How's it going to be? It's a bad bond angle for an sp carbon. Is it really sp? Well, no, because sp would be linear. That's what sp means, linear. Most of it, half of it at least. It ain't linear. Okay, we showed mechanism there. Basically, essentially, the hydroxide is not going to come in here and do a nucleophilic addition to give an anion like you do with NAS. Not going to happen. You can only do that when you have a strong electron withdrawing group ortho-apara. Instead, though, it acts as a base and it actually takes one of these hydrogens. Next door, we have dipole here, has slight acidity. Not much, but enough that if you can, very forcing conditions, we can do acid-base chemistry. And we can leave the anion there, right? What we got here? Hydroxide. These electrons take the H, these stay behind. Okay? This carbon is sp2. Again, we know we can do this with the H on an sp carbon, right? We've done that a lot with alkynes, okay? The chlorine or the fluorine or something over here, particularly fluorine, really pulling. Usually a potential leaving group is going to be some electronegativity. What helps pull and stabilize this. How do you stabilize an anion? Pulling electrons away. So it has hybridization, it has to do that. This thing, now the chlorine, you can do this two different ways. I'm going to do it a little bit differently and then get there. Carbanion. Carbon's like, I don't like being minus. Well, why'd you do this, carbon? Well, you made me because you forced me to do this. Okay, carbon. Well, how about if I just leave? I like to be minus. If I just leave, what will that give? Well, that's just still there. But what's now here on this?
Oh, positive.
A positive plus Cl minus. Okay? Cl loves to be minus. So not only is this good, but now your benzene is back to neutral. Because it's a plus and a minus, okay? So this seems reasonable. Going down here. Well, there's your benzyne. That's just a resonance structure of benzyne. If you want to actually show the benzyne, we can do resonance structure. These electrons move here. What does that do? We now have triple bond there. That's just a resonance structure of your benzyne. That is your benzyne. Now books will do this differently. We could have just right here, instead of showing that leave, that both arrows at once. And last time I moved these in and kicked that off. And gave this directly. If we try to draw a structure of this, well, p orbital, we have pi bond there. One electron, one electron. There's the pi bond. I'm not going to show the overlap. But this here is still sp2 with one p orbital. The lone pair here is in a hybrid. It's a good structural consideration. In the handout, it shows a little bit of this. What hybridization do you expect up here for this? Or if you want to look at it here, hybridization here.
SP2.
For that carbocation.
SP2?
Okay.
SP2?
Why sp2? How many regions around it?
3.
3.
I mean, I see a double bond region and a single bond region. There's no H there. What hybridization do you expect?
SP2.
2 regions is
SP.
sp. Is it sp?
No.
Why not?
It,
Because sp would be linear, and it can't be linear. It's actually sp2. Even though you would expect sp. It's sp2. It has a p orbital. But then it has a hybrid. I mean, this is a hybrid. Lone pairs in a hybrid. That's actually an empty hybrid orbital. And what you have here is the second pi bond here. Not really a pi bond. Officially, a pi bond is, well, usually pi bond is side-to-side overlap of p orbitals. This is not. This is side-to-side overlap of hybrid orbitals. Or again, it's still a pi bond because it's side-to-side overlap, but it's actually hybrid orbital overlap. And that's what I was trying to show here. See, each one of these is trigonal planar. It has to be. It can't be linear because it's in this ring. So it's trigonal planar. And trigonal planar is sp2. So it's a unique triple bond. It's very weak. And a lot of times, this resonance structure, as often are, or resonance structures of molecules, could be used in your mechanism here. Okay. So do you believe this Benzyne? When this mechanism was first proposed, and then what happened next? We had water, right? You got the mechanism from last time. You know, water comes in. Importantly, at this point, which carbon does it attack, top or bottom?
Either.
It's symmetrical at this point. And this can attack here and move electrons here, or the other way around. And that led to, right, you got this already, this, and that's minus. We could have gotten to the same structure by just adding, well, it would have been flipped. We would have had to add it up here, down here. Proton transfer gives us the phenol. The phenol is then deprotonated. Because if you knit a sweater in the pool, it's going to be wet when you're done knitting it. You're going to have to dry it. All right? If you make an acidic compound under basic conditions, it's going to be in the basic form. We're going to have to work it up with acid to put the proton back on, and we get the phenol, OH instead of chlorine. Okay, for a long time, people didn't really believe this mechanism, and people's proof, hey, can you give me more proof that this is the mechanism? Would you like more proof? I agree, me too. Benzyne will react in a Diels-Alder reaction. And if you take a benzyne that's been formed and bring in a diene, right? What type of reaction can take place? We can get a 4 plus 2, and that would equal what? 6. These electrons here, these electrons here, these electrons here. What would that give? It'd give the product shown over there, right? But that's left with just a double bond, because here it was the second pi bond that reacted. You see your air movement? Okay? And such a product can be obtained. So if you're able to get this product, and you know Diels-Alder chemistry, you would think, well, it's coming from this, and this is indeed what I'm proposing as an intermediate above. So benzyne will react as a dienophile in Diels-Alder reactions. So that sort of supports the notion that this is indeed the structure, yeah? Additional proof. A classical experiment in the 1950s chemist by the name of John Roberts at MIT, trying to prove this mechanism, took bromobenzene, in which the carbon of the bromine was labeled as a C13, and did a reaction with potassium amide, the anion of ammonia, right? That's K plus. This is what? NH2 minus. It's a very strong nucleophile. I mean, we use ammonia as a nucleophile. Imagine the anion of ammonia. It's a very strong nucleophile. And you can actually do this chemistry at cold temperature. Minus 33, which is liquid ammonia. Okay, that's an L. Liquid ammonia, minus 33. That's the solvent. And the product that he got here was the NH2 nucleophile substituted the bromine. But quite interestingly, and this was 50-50, half the molecules of nitrogen was on the C13 carbon, but in half the molecules it was next door to the C13 carbon. And you can tell that because one carbon is C13 and the other one is C12, and you can determine that a number of ways. So, what does this prove? First off, it proves that in this mechanism, it's not just displacing the bromine from that carbon, because if it was, then it should be all that product, right? There's something else going on here. How did we get the nitrogen bonding to the neighboring carbon? Well, it's actually benzyne. This mechanism supports benzyne because what is the mechanism? Since I've got my double bonds drawn in this way, I wish I would have drawn them the other way. I'm going to take this H over here instead. We could actually take either one. Anion takes the H, right? Leaves the electrons here. We have boom, boom, boom. We've got bromine. That's our C13. We've got anion here. Plus ammonia. What can happen to this anion? The bromine can just leave, yeah? Bromine's like, hey, I'll be minus carbon. You don't like being minus. We can do this two different ways. I'll do it this way this time. Electrons in, kick that off. What does that give? It gives the benzyne, right? But this carbon over here is C13. Now, everybody seeing where we're going here? Then the ammonia comes in. Nucleophiles will react with this. Electrons come in and which carbons are going to react with, left or right?
Either.
And here's the answer. Either one. It's symmetrical. And the fact that it's C13, I don't know if that influences it. I don't know if it's exactly 50-50. Does the fact that this is C13 affect the nucleophile? Does it see that as different here? I don't know. But I'll just do, to get to that one over there, can it do either? Which one? How about this one? And move these here. What does that give? That's going to give anion here on the carbon 13. Still double bond, double bond, double bond. Here we have the ammonia added. What's this going to do? Minus, right? What's going to happen with that?
Proton transfer.
Proton transfer. Carbon needs an H, nitrogen wants to lose an H. Everything go neutral. Proton transfer would give what? H plus transfer, and there you go. So does this experiment support the mechanism? Question.
So is it possible for like the H on the NH3 to just transfer directly to the anion instead of like it having to protonate and deprotonate from like the solvent? Does that make sense? Like the book used the solvent
Either solvent, we have ammonia. It could. This could take an H from ammonia, and then the anion could take an H. Or it could be two different molecules. The anion of one molecule takes the H off of the nitrogen from another molecule. So that would be intermolecular. It could be a variety of ways. That's why I often just say H plus transfer.
So it can be intramolecular.
Well, that would have to be a 1, 2, 3, 4, a 4-member transition state, and that's sort of strained a little bit. Possible. But again, it could be a variety of ways, and we often just show this as H plus transfer. We'll be doing it many times moving forward with carbonyl chemistry. And when you get in biochemistry, you won't even call it, you get to biochemistry, the H is just going to be moving around, and you ain't going to say H plus transfer. You got to know what's going on there. H plus transfer. Yeah.
Are we still doing like the H plus lookup still to get rid of all the extra in H2?
You don't need H plus workup here.
How come?
Well, why would you?
Well, last time we had like,
That's because we made an acidic molecule under basic conditions, and if you knit sweater in the pool, you got to dry it.
okay.
Okay. What conditions are we under here? Ammonia is basic, slightly basic. Is the product acidic?
No.
No. So you don't have to dry it. If the product was acidic enough that ammonia would deprotonate it, ammonia is not going to deprotonate aniline. So no, you wouldn't have to do it. You just let the ammonia evaporate. Warm it up, ammonia will turn to gas. Or you can quench it with some acid. There's ways, instead of letting the ammonia evaporate, if you quench it with acid, then you're going to protonate your product. So, question?
If you have an ethyl attached with a leading group like iodine attached to the nitrogen, could that lone pair go and kick off the iodine, and the iodine take the H?
What do you mean iodine?
An iodine attached to a ethyl attached to the nitrogen on that entire compound, and then the
You mean
lone
here?
pair. Yes, sir.
Something like this?
Yes, sir. And then that attacks the benzyne, and then the lone pair attacks the carbon on the iodine and kicks it off, and then the iodine takes the H from the.
You would then make a ring here.
Yes, sir.
Yeah, you could. I can see something like that. Because that anion there, the problem is not if there's acidic proton. Because proton transfer is going to happen before anything else, because acid-base reactions are instantaneous. SN2 takes a little more time.
Okay.
So you got a proton there that is going to ruin this nucleophile.
Can you protect it?
But if there were no protons here, if they were like methyls or something, well, you got to have. Okay, in theory, you could devise something there. We'll see some reactions like that below. Basically, this experiment was very important for helping determine that this was in benzyne. And today, this is the sort of known mechanism until someone disproves it. Maybe somebody here can disprove it one day. But for now, this is the best thing, the best theory. Okay? Benzyne. Because you would not do NAS here. The theory is you don't do NAS with such a molecule because there's no ortho-para director. Or, I'm sorry, ortho-para strong withdrawing group. To activate the bromine for displacement by NAS. Benzyne's the only other way. Okay. Up top we had isomers, but that was just because we had a C13. Here's an example of getting isomers with other substituents. If you take parachloroaniline and do the same reaction, you get two products. One of them, the nucleophile, has directly displaced the chlorine. The other one, somehow the nucleophile is next door. And this is two different products. What is this? Two common names. What? 4-methylaniline? Or 3-methylaniline? How do you get two different products here?
Which side of it?
Benzyne. Benzyne is the key intermediate, and then the ammonia attacks either one. By the way, in the above, I had everybody realize I just flipped the molecule around when the product was drawn. I was working on one side. Okay. Where are we going to make benzyne? Now again, my pi bonds are drawn over here. So if you want to do it over here, of course these pi bonds aren't really localized like that, right? Of course the pi bonds are really all the way around. But in terms of mechanism, we want to kind of have them there. And so the benzyne again was here. And then the ammonia could add either here or here. And of course, if I made the triple bond over there, it's the same as this. All right, two different products. May or may not be 50-50. Okay? Because one may be favored over the other. We may mention why a little bit later. Okay? For example, here. If you take this, sodium hydroxide, 300 degrees, then an H plus workup, that is just workup, two major products. What are the two major products? Isopropyl. I'm going to get this product plus what product? Reasonable that I get those two phenols from benzyne. In this case, one of these might be more favorable. Which one do you think may be?
Maybe the meta.
Why meta?
Let's do it.
Why there?
To attack the benzyne, it would be easier on the other
Because when you attack the benzyne, what attacks it here?
than the OH.
Water. Because hydroxide takes an H, becomes water. Water attacks here. Okay? Because the water's all around. Here I come. You know. I get kicked away by this group here. But up here, there's nothing going to kick me away, and it's like, you know, boop, incoming. This is going to block sometimes. You're going to have no blocking up here. So this may be more favored here, and it's not 50-50. So even though your leaving group is on this carbon, your nucleophile ends up over here, benzyne.
So why like the differences in temperatures, like extreme?
Well, NH2 minus is a very strong nucleophile. Hydroxide is not as strong. All right? Because hydroxide is a better, more electronegative. It's able to have minus, hold B minus. And if you go back to the first page, we said it takes a high temperature or very strong nucleophile. NH2 minus is an example of a very strong nucleophile. How about the one on the right over there? Three major products. Why three over there? That is a benzyne. Why three?
It's not symmetrical.
You can take two H's on either side of the chlorine.
Why?
You can take an H on either side of the chlorine.
Because there's two different benzynes that can be made. Which H is the base going to take? It could actually take either one. In the previous examples, the neighboring H's were identical because of symmetry. Okay? Two different benzynes. If it takes HA, we're going to get that benzyne. If it takes HB, now again, see these are drawn in. We can get triple bond here. That's just because you want to start with your pi bonds drawn in differently. Of course, neither one is correct. But you can end up with a triple bond over here, if I can draw a ring. And if the triple bond's there, the other two would be here and here. Two different benzynes. Then the ammonia comes in. Here it can come in here or here. Up here it can come in either here or here. Both of them, the ammonia is going to end up where the chlorine used to be. But this one, you can get ammonia here. Okay? By the way, if that was methyl, it'd be anisole. Pretty sure this is called phenol. Don't even know that. The phenol, well, we're going to have aniline. We can get this, right? Almost don't want to draw these, but we would also get this. But we could also get all three. Because there's two different benzynes. Giving you three different locations to attack. Because this is the same location. Three different locations to attack because of two different benzynes that are possible. Which is going to be favored? It's hard to know. We can maybe... Which H is more acidic? Because the rate determining step is removing the H usually. I say usually there's a problem in the workbook where rate determining step sort of varies depending on what the leaving group actually is. Hard to know. Let's move on. Hard to know what the major product would be. This chemistry can actually be done stepwise. Above, it's going to be hard to do it stepwise because once you make the benzyne, you got something there that's immediately going to react, like ammonia. And so you can't really stop there. It's going to continue on and give you products. If you use a base like N-butyl lithium, you can kind of stop here and add something else. And you're not going to isolate this. But you can then come in with something else other than what you have here, because N-butyl lithium, right, we take the H, I'm not going to do complete mechanism, but we would get to, depending on how many intermediate, you would have that plus what? What's the fate of this? Just butane, right? We took an H. But see, butane will not react with your benzyne. Butane is not a nucleophile. It has no lone pair. It's not, and so there's nothing to react with your benzyne. You do this. So here we can come in with other things. For example, you throw in something like this and do a Diels-Alder with a diene and have that be a dienophile. And the triple bond here would be your dienophile, and you should be able to show a Diels-Alder product. Let's look at this. This is actually some common chemistry. You may not see this in the textbook, but it's very fundamentally straightforward chemistry. What can happen if we bring in, what is this, methyl magnesium bromide? What can happen here? Well, this is a source of what? Right, the methyl anion. Could it react with benzyne?
Yes.
Yes, benzyne is electrophilic. Nucleophiles react with it. So this could come in here and add here. Electrons up. We now have a methyl here, and this is now what?
Negative.
Anion. Now, that's just going to sit there unless we supply a proton. Because there's no proton here. But what if we throw in something like ethyl bromide? What could happen? We could do some chemistry like this. And there's your final product. What is that? Ortho 2-ethyl toluene? I think it'd be called 2-ethyl toluene. But that's sort of sequential, stepwise. Where above, everything's all mixed together and your nucleophile's there. Okay? Question?
Oh, I mean, I was just like assuming that from there you could just do like pretty much any like addition reaction as well. You can-
From what? This
From the
anion?
product.
Hmm?
The product you got.
Product over there? What do you mean addition reactions?
Well, I don't know if you wanted to add.
Well, benzenes don't do addition chemistry.
Well, okay.
Alkenes do.
Okay.
Benzenes actually do substitution.
Right.
That was in the very first page of the EAS handout, or really back to aromatics. How can you determine if something's aromatic or not? We'll do substitution, where an alkene will do addition. You can do EAS chemistry there. Problem is you got two different group 2s and you have no predominant director there. Is it going to go ortho pair to the ethyl or methyl? Either. There's no dominant director. It's going to be a tough time. If you brominate this or something, where's it going to go? Okay. Sequential. By the way, another way to make a benzyne is from dibromobenzene or dichlorobenzene, reacting it with magnesium. Can you envision what's going on here? What's going on here? What does magnesium do to like a
Grignard reagent.
Okay, let's look at Grignard. Let's consider just one Grignard being formed. What can happen here? Well, keep in mind the Grignard is really what? Br minus, carbon minus. If we show this as minus, like it really kind of acts as, what can happen here?
It's off.
Boop. Kick that off. And you'll get benzyne plus what? What else is formed here if you balance this out?
2
MgBr2, magnesium bromide. Magnesium plus was made with the Grignard. 1 Br minus was made with the Grignard. When this leaves, you got your second Br minus. That's a tricky way to make a benzyne. Probably not in your book. Don't tell anybody I told you either. Okay? Our secret. Tricky little way to make a benzyne. Because up here you're using a very strong base that's a little bit costly and a little bit hazardous to use. Down here you're just bringing in magnesium metal. All right, and there was some of that on the sequential on the bottom of the warm-up page. Down here we had an epoxide at some point, yeah? Okay, benzyne's some fascinating chemistry. We get a product from this one here. By the way, product of this reaction. Can you name the product?
3-nitrophenol or 4-nitrophenol.
Product here. What's happening?
It's just a substitution. Alkynes.
Name of the product here?
Or not alkynes, it's,
Oh,
4-nitrophenol.
4-nitrophenol of the product.
4-nitrophenol, yeah, why not?
Wait,
4-nitrophenol, yeah? What took so long?
I didn't know what you're asking. Until like they registered.
Okay. I just asked what the product,
Right.
product was. Are you gonna get any 3-nitrophenol?
No, it's just.
No,
No.
because you don't need a benzyne.
Tell me again?
You don't need a benzyne because you have the nitro para.
What's the mechanism for this,
NAS.
NAS?
Yes.
mechanism, Jen?
I mean, I would say it's an NAS reaction, but I'm kind of thrown off by having a strong withdrawing group para to the chlorine with the harsh conditions. Like, I feel like you haven't given us an example like that yet. So I don't know if you're trying to say that this is like, that a benzyne reaction is still possible if you have a group, a strong deactivator para to the leaving group.
This is going to be NAS.
Okay.
NAS. We're going to have this product. We would have to work it up with acid because this is acidic. How's it going to exist under basic conditions? And so there's a workup here. Now this is it. It's NAS. Why is it NAS and not benzyne?
Just
Because you have that nitro para to the leaving group.
Yeah. Couldn't we do benzyne though?
That's kind of my question. I don't know.
Okay, good. Anybody else?
Wouldn't it? It's just. I feel like it's just because of just because it's withdrawing.
Okay, here's what I want you to know. If you can do NAS, do NAS. Benzyne is a very hard to do mechanism. You would never do benzyne instead of NAS when you can do NAS. All right? NAS is much easier, as long as you can do it. If you can do it, do NAS. The 300 degrees is just, it's meaningless. That's going to make NAS even easier. You would never do benzyne instead of NAS. That's just what I'm trying to get at. This is only going to give this. Does NAS give isomers? No, NAS you just place directly the leaving group. The nucleophile is going to be here. That's NAS. Okay. You only do benzyne when you can't do NAS. Okay? You would never do benzyne here. That's the answer. Never do benzyne. If you can do NAS, do NAS. Okay. Did someone get a product here? This is an important product in terms of drug. What can we do here? Somebody have a product? Any chemistry possible here?
Yeah. The bottom F fluorine gets replaced.
This fluorine, which is a great leaving group for NAS, it's actually the best halogen for NAS. Is either one of these activated by having a strong electron withdrawing group ortho or para?
Yes, because it's para to carbonyl.
Yeah, that's connected para, carbonyl. How about this one?
Yeah, it's a
No, para is a nitrogen. That's not withdrawing group. Basically, this is your strong electron withdrawing group, but it's para to this. This is the one you're going to displace. Product here. Now, this has two sites. You got to be careful how you do this, or you're going to get reactions on both ends. Product here is Everything's the same over here, yeah? That's an F, and then here we're going to have the nitrogen. If we just do a single reaction on one end, be that. NAS. If we balance this out, what else is formed here? Meredith, what else is formed here?
Meditative.
HF, yes. That's an acid, though. We're under basic conditions. How's your base going to exist? What can happen here?
Maybe defermented.
As this is formed, these basic nitrogen is going to react here. It's going to ruin this. It will no longer be able to react over here. How can we compensate for this?
Two equivalents.
You can use two equivalents. That way, instead of making HF, you're going to make you can just have that salt there. So one equivalent to react and the other equivalent to react with the HF. Or you can include some other base, such as like maybe potassium carbonate or something. Okay? You also have a slight problem here because you've got an acidic proton here. Basically, there's some acid-base chemistry here you've got to be careful about and how to work up your product to get it in the neutral form. This is Cipro, antibiotic. Or Organic 1, I gave you our DQ page from test 1, had a lot of Cipro questions on it. No, Cipro is made here. One of the final reactions of making Cipro is this NAS reaction, displacing one of the fluorines. But only this one, though, because it's the only one that's activated by a strong electron withdrawing group ortho or para. One last example here, some drug synthesis here. There's an NASF here. What are they doing? A nice fluorine there, nitro group ortho, nucleophile, making that bond there, the amine displacing the fluorine by an NAS. Then, by the way, they come back and they reduce the nitro group to the amine, but then the amine reacts with the cyano group. And so it's sort of a two-step process here. By the way, they're using tin chloride. That is possible with tin. You can use tin metal. But you can also use tin chloride. Because this is 0, this is 2 plus. Tin can go to 4 plus. And so the tin can be further oxidized. Thus, it serves as a reducing agent. Okay, guys, about our time, yeah? This is in the material. We'll begin test 3 material on Friday. We'll have a review session at 7:15 on Friday morning. We'll confirm the test format for Monday. Very same format as always. Nomenclature, yeah, was by video. Any questions about lab this week? Basically, it's kind of opened up for you to do kind of your choice of reactions. And certain reactions have a choice of which substituent to use. Your choice. Okay, we're about out of time, guys. Have a good day. See you on Friday, 7:15.